Also from my side, I want to thank the organizers for taking me in as a replacement for Markus. I want to thank the team that's taking care of all the setup, which is, as Jadwiga already yesterday said, really nice. I also saw the Instagram posts and was pretty impressed. We look really good. Okay. Today's the last lecture. I just want to recap what we learned in the first two lectures. So we learned the basics of quantum error correction and the quantum circuit model, where this was the leading example, the encoding of a 3-qubit repetition code, which we then later extended to codes that can actually correct for arbitrary single-qubit quantum errors, using the framework of stabilizer error correcting codes, which in a minute I will recap in a little bit complementary perspective. Then we learned about topological toric and surface codes, which encode the quantum information in global features such that you can protect against local noise, which was a little bit more physical perspective, and started to talk about logical gates. We learned about the teleportation-based quantum gates, and today we're gonna continue that story with other logical gates, in particular the C0 gate. Then I'm gonna flash some principles of fault-tolerant circuit constructions, but there's also gonna be talks about that next week, so it's gonna be very high level. I'm gonna have some references, so if you're more interested, you can read that up. And then I have a final section on scalability, or on new approaches, and a little bit about scalability, in particular quantum LAPC codes. Again, we'll see how far we come, but at least this last part I want to flash a few of more modern approaches. Again, interrupt at any time. You can also use this poll bot. I will actually put it up on my phone so I can check whether there's questions there. Maybe it's working today. Yes, perfect. Okay. Okay, before we start with the slides, I want to repeat a little bit the 3-qubit repetition code, where we start with some arbitrary state. And then we use this small circuit to encode it into a state, into a logical state. Where the basis states were 0, 0, 0 and 1, 1, 1. And this code we then also looked at as a stabilizer code with stabilizer generators Z1, Z2 and Z2, Z3, because those were operators that stabilized this code space. So they were +1, those states were +1 eigenstates of those operators. Now the perspective I want to convey now, because this will be helpful when we will talk about how we can implement a logical C0, is that that same perspective, but going step by step in time. So if we start with this 3-qubit state here, which is just psi O times 0, O times 0, then we can also write down stabilizer and logical groups for that, or sets of logical operators and stabilizer group. Now, it's an arbitrary state. So in this arbitrary state, this encodes our logical information. So the logical operators are x1 and z1. These two states, 0 and 0, those are known state. Those are known states and stabilizer states that are fixed, which have one stabilizer. Can someone tell me what the stabilizer of this state is? What's the operator that where this state is has a +1 eigenvalue? Hadamard 0 is plus, but that's not an eigenstate of Hadamard operator. It's the Z, right? Because Z0 is plus 1, 0. So we have two stabilizers, Z2 and Z3. Now, when we go one step further, we apply a C0, and we could do this in the perspective of the state vectors, but we want to work with operators in the stabilizer formalism. So we can also think of how these operators transform. Now, I've shown you on some slides the other days that, for example, if I conjugate if I have an X on a C0 and a C0, then this would be the same as if I have two X's after the C0. Why is that? Yeah, you can just calculate and make and make yourself clear about that. You can also the calculation would be X then C0. It's 0, 0, O times identity. So if the control qubit is in 0, then we don't do anything. But if the control qubit is in 1, then we apply an X. And if we conjugate the X with this C0, then we will just get X1, X2. So we can think of an X operator as flowing through the C0 and spreading to those two qubits. So the logical X operator in the next step would be X1, X2. A Z operator can probably barely see the color, but a Z operator commutes with this control because it's both in the Z basis. So this just goes through and stays a Z operator on the first qubit. The stabilizer operators, we can also track them through the circuit. And there we can do the same calculation, just with Zs. And we will see that a Z on the target qubit will propagate to a Z on the control and the target qubit. So the Z2 will propagate to a Z1, Z2. The Z3 in this time step still just stays on the Z3. Then finally we do the last C0. This XX operator propagates to an X1, X2, X3 operator. The Z1 operator commutes through. Z1, Z2 also stays Z1, Z2. But now the Z operator on the last qubit will propagate onto the first one. And we will have Z1, Z3. So the final stabilizer group on these three qubits at the end of this Clifford circuit, these are all efficient transformations because they're Clifford, is Z1, Z2 and Z1, Z3. And the logical group is X1, X2, X3 and Z1. Now these are exactly the logical operators that we've seen before. What about the stabilizer group? There's something different from the one how I defined it here. Is this a problem? Or is this the same code anyway? So I've been a little sloppy with how I talk about this. I call this a stabilizer group, but it's not the group yet. It's just generators of the group. So any product of those is also a member of the group. And if we multiply those two, out comes Z2, Z3, which is exactly this operator which I've specified before. So these are two completely complementary perspectives, but it's very instructive, I think, to think about how we can build up the stabilizer group of the code from the very start. And then it also makes sense that we encode one logical qubit because we started with one state with an arbitrary, which is arbitrary. So we had these logical operators, which these physical logical operators, which encoded into these. And we had two fixed states, which are the two stabilizer generators, which can help us with error correction. Okay. Now, on the other side of the board, I want to introduce yet another way to encode the repetition code. By starting with, how are we going to do that? Yeah, same way. Start with psi 0, 0. And instead of doing this unitary encoding circuit, we immediately measure those stabilizer generators. I will do this as a black box for now, because the details are not important. We could do this by projective measurement. We could have some physical mechanism that implements this Z1, Z2 measurement directly, and then the Z2, Z3 measurement. And I now want to use the same kind of philosophy and go step by step and track the logical and the stabilizer operators. But now we have these measurements. So there's like an addition there. We just have unitary operations. Here we now have measurements. How do we take care of those measurements? Yeah, we again start with the set of logical operators, generating set of the stabilizer group, which is x1, xz, z1, and z2, z3. Okay, if we measure a z1, z2 operator, what's the measurement outcome of this measurement on this state? We can calculate this. So we do a projective measurement. So we start with psi 0, 0, 1 plus -1 to the measurement outcome. Let's see, I haven't prepared this, so let's see how this is gonna work out. Z1, Z2. Let's do it like this. A sec. Gonna start by expanding this. So we're starting with alpha 0, 0, 0 plus beta 1, 0, 0. So if I measure Z1, Z2, then I'm gonna get. Okay, I will have to do it differently. I will not start with an arbitrary state. I will start with a 0 state, because then it's easier. I'm gonna start not with a 0 state, but with a plus state. So, okay. So I'm gonna start with 1 over square root of 2, 0, 0, 0 plus 1, 0, 0. And now we can check what happens if we measure Z1, Z2. So we're going to do projective measurement, and it's going to have what outcomes? Can someone tell me that? So the expectation value of Z1, Z2 is we're going to get a minus sign out of here. So this is 1/2 for this part, and minus 1/2, so it's 0. So we're going to have +1 or -1 measurement outcomes with equal probability if we do a projective measurement. So if I put in a projective measurement, I would usually write psi and then 1 plus -1 to the measurement outcome, the operator half psi to get the probabilities, and this would give me 1/2 for both measurement outcomes. Okay. So in this case, I have to make some space here. I will actually not start with a logical group x1, x2, because this is not stabilized anymore by z1, but only by x1. And I'm going to measure z1, z2, which commutes with z2 and z3, but it does not commute with x1. And because it does not commute with x1, it will kick x1 out of the stabilizer group. So there's no more x1 in the stabilizer group because of this, because it doesn't commute with this one. But we will add of the logical group, but we will add z1, z2 to the stabilizer group with the sign of the measurement outcome, because the post-measurement state of the z1, z2 measurement will be an eigenstate of z1, z2 depending on the measurement outcome. In the next step, we will measure z2, z3, and we can do the same thing. We will get some, in this case, we will actually get a +1 measurement outcome because z2 and z3 is already in the stabilizer group. So then we add z2, z3 to the stabilizer group. And then just by measuring the stabilizer generators, in the end, the stabilizer group, now the logical group tracking did not work here in this example, but the stabilizer group in the end will be generating set of the stabilizer group will be -1 to the measurement outcome z1, z2, and z2, z3. And if we have this stabilizer group, then we also know that we will have some logical group. So yeah, so instead of doing this unitary encoding, we can also encode by just measuring those two stabilizer generators on our state, and we will get put in a eigenspace of those stabilizer generators. If the measurement outcome is random, then we will just have a minus sign over the stabilizer generator. But we could fix this, for example, by applying an x1, then we would get rid of this. We would get rid of this minus sign. Okay. So now this I just wanted to to add to our discussion from before, that instead of doing a unitary encoding like this, you can also prepare your code by measuring the stabilizer generators of the code. Okay, any questions to that part? Okay, then we will talk about how we can now perform a logical CNOT, where this perspective will help us a little bit in order to entangle our logical qubits. Now, quick reminder, we've seen it now a few times. What does the CNOT do? If it's in 0, the control qubit, we do nothing. If it's in 1, we apply X on the target qubit. And we now want to do this on the logical level. And as an example, we will use now the surface code. So we have those two lines encoded in surface codes, and we want to perform a logical CNOT. Now, one way to do this, and this actually works for every code that only has X and Z stabilizer generators, is to do a transversal CNOT. Transversal means that we just couple every qubit of our control logical qubit to every qubit of our target logical qubit. And if they're in the same code, then we just use the qubits that have the same index. Now, why does this work? So the goal is that our logical operators simulate the same propagation rules that I've shown you here. So we want a logical X operator to propagate to a logical X1 operator to, after our gate, be an X1, X2 operator. We can verify whether this works. So let's say we have an X1 operator sitting on these 3 qubits because we have a 3-qubit repetition code. Then we can use these physical rules and propagate it down like so. And we will see that indeed, in the end, we will have X1, X2 logical. Okay. I think you believe me that the same thing works for the Z operator on the first qubit, the Z operator on the second qubit. So transversally, we can at least now transform the logical operators in the way that we want the physical operators to also transform. Now, a second condition for logical gates that I've shown you yesterday is that the logical gates keep the stabilizer group invariant so that we still have the same code that we've been working before, and we can do the stabilizer measurements and quantum error correction. Now, how does this work here? If we have some stabilizer, X stabilizer, for example, that has support on these 2 qubits on the boundary of a surface code, then this also propagates down. So we have a mixed stabilizer. So a stabilizer that is X1, X2 on the first becomes a stabilizer X1, X2 on first and X1, X2 on second. Now, is this a problem? No. This is not a problem because on the target logical qubit, we also have the stabilizer X1, X2. And this stabilizer, let's put it in another color. This stabilizer does not propagate through the CNOT because it commutes. This is an X-type operator and this X. So this just follows through here. And we have learned that it's a group, so we can choose our generators. So instead of, for the new code on the right side of this gate, choosing this as a generator, we can also just choose the product, such that, again, we will just have X1, 1, X2, 1 on our first logical qubit. And the stabilizer group is indeed kept invariant by this operation. Okay, and this works for any code where the stabilizer generators have only X or only Z type, because then we can do the same, we can use the same reasoning or the same calculation that the stabilizer group stays invariant and the logical operators transform correctly if we use 2 copies of the same code. So if we wanted to perform this in real life, we could just take one surface code like this, put one on top of it, couple those here transversally, and we have our CNOT. Now, is this practical? Not really. We have started with historic code that lives on the torus, and we said, yeah, this is maybe not feasible in a lab, and now I tell chip people to build a chip that can do this. They will think I'm crazy. So we'd rather want to put a CNOT on 2 surface code that live next to each other in 2D. And the way to do this was introduced in 2012, and it's called lattice surgery. Lattice surgery uses gates based on teleportation and uses ancillary logical qubits. So here on the right, you can see the CNOT that will be implemented by employing an ancillary logical qubit in 0 and then performing joint logical measurements. So here, sec. So here we have this ancillary logical qubit, and then we will perform joint logical XX measurements, joint logical ZZ measurements. I don't know why this always happens. Another logical measurement on the ancilla, and then some Pauli corrections in the end in order to perform this controlled knot. And I will now in the following show you how this circuit on the right will indeed perform the CNOT by using this similar approach to this one here, combined with the measurements on the right, showing that indeed the logical operators transform correctly. Okay, I will keep this up, and I will delete this up here. Okay. So on the right, we start with the control qubit and the target qubit, which are in arbitrary states. So they have X and Z logical operators. C now stands for control, T for target, and we have this one logical ancilla which is in 0, so it has a Z logical stabilizer. Right, so in addition to all the stabilizers they all have, the control, target, and logical qubit, this logical ancilla also has a Z logical operator as a stabilizer, because the 0 state is stabilized by the Z logical. Okay. Now, the first operation we're going to do, the 1, that's 0, that's where we start. 1, we measure XX. Now, if we measure XX, no matter what the target qubit, which state the target qubit is in, because our ancilla is in Z, and we measure X ancilla, X target, logical, these anti-commute. So we will get some random measurement outcome M1, and we will add this operator, logical X ancilla, logical X target, with the corresponding sign that we measured to our list of operators of our code. Now, if we measure this one and something anti-commutes, we have to kick it out of the stabilizer group. And everything else that anti-commutes, so there might be many elements that anti-commute, but if 2 elements, if let's say, let's do it in a very general way, if we have operators A1, A2, A3, and we measure a 4th operator A4, which anti-commutes with A2 and A3, and potentially many more, then we can always choose one representative anti-commuting operator and multiply it to other of these operators if they form a generating set of the stabilizer group, because then the operator A2 times A3, which is also part of the stabilizer group, right? Because it's a generating set, so products are also part of the stabilizer group. This will indeed commute because both A2 and A3 anti-commute. And then twice anti-commutation gives us commutation again. So in order to find how the full stabilizer group transforms, we just have to kick one representative out of this anti-commuting operator out of the stabilizer group to replace it with the one we just measured, and multiply this to all the others that anti-commute to make them commuting to find a new generating set of the new stabilizer group. So let's do this here. ZA anti-commutes with XA, XT. So we kick it out. ZT, the target logical Z operator, also anti-commutes with XA, XT. But if we multiply it with ZA, XA, XT, and ZA, ZT, they commute because they anti-commute twice. Question? We don't measure the zero state in the X spaces. This is a joint logical measurement. So we measure, so this could be implemented on the physical level by getting another ancilla in plus, performing control X, and then measuring this in X. And the state here is alpha 0, 0 plus beta 0, 1, which is only stabilized by Z0 and not by anything else. And if we measure XX and stabilized by ZI, ZI and XX anti-commute, so the measurement outcome will be random. So if we would measure, right, so for the projective measurements, you have to do 1 plus minus 1 to the measurement outcomes times your operator on your state to get the probabilities of measurement outcomes. And if you do this calculation, you get 1/2, 1/2. Plus 1 or minus 1. And here it's 0 and 1, yeah. Yeah. That's the computer science indices, which I also mix up sometimes, similar to other people. Okay. Okay. All the other operators, XZ, Z, X control, Z control, and X target, they commute with this one we just measure, so it survives this measurement in this, they survive, quote unquote, this measurement. Okay, next. Next we measure Z control, Z ancilla. And again, it's an operator that anti-commutes with element in the stabilizer group. This one here, namely, because ancilla and ancilla, Z and X on ancilla anti-commute. So it will get a random outcome, minus 1 to the M2. And minus Z or plus ZZ will be in the stabilizer group afterwards, depending on M2 and the measurement outcome. And we do the same game. So we remove one element of the stabilizer group, which anti-commutes. We're going to take this one, and we're going to multiply the other anti-commuting elements with this. Now, the only other anti-commuting element here, this is a target, is the X control. So this is going to become -1 to the M1 x ancilla x target x control. Z control stays as is, x target stays as is, and Z ancilla Z target stays as is. And then finally, in the third step, we measure logical x on the logical ancilla. So x ancilla. And then we again check, okay, with this element in the stabilizer group, it anti-commutes. So it's going to have a random outcome, -1 to the M3, so that minus or plus XA is in the stabilizer group after measuring it. We kick this element out of the stabilizer group and multiply all anti-commuting elements with it. The only anti-commuting element is this one down here, ZA anti-commutes with XA. So that in the end, we're going to have -1 to the M1 X ancilla, X target, X control, Z control, X target, and -1 to the M2. Z ancilla times Z ancilla annihilates, so we just have Z control, Z target. All right. And now the very last thing I'm going to do is, I'm going to remind us where the logical operators were. These were those, and those. And the stabilizers were here, 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 and here. And as we've learned, we can also multiply stabilizers into logical operators to get new representatives. I don't like this ancilla here. I've also probably destructively measured out this ancilla because I don't need it anymore. So I will multiply this in there to get rid of this ancilla here. And we'll have to multiply these two as well so that I get M1 plus M3. And my the final transformation of the logical operators looks as such, which should remind us exactly of the way that we said in the beginning we want the logical operators transform in order to mimic the way that physical operators get transformed by the physical CNOT. The only difference now is that we have those measurement outcomes here in the front, but we can fix these. We can fix these signs to the correct signs because, as most of you probably know, and I've already shown once or twice, xzx is minus z, and zxz is minus x. So we can fix these signs by, depending on the measurement outcomes, apply these Pauli corrections that are shown there on the right. So here on 4, you can see that on the control qubit, you apply Z1, M1 plus M3, and this Z1 on the control, M1 plus M3 will fix this sign to always be +1 independent of your measurement outcomes. And the same with the X correction on the target qubit. And here is also shown a Z correction on the ancilla qubit, which will fix the sign of the stabilizer, logical stabilizer group. But as I've said, potentially we don't use this ancilla anymore. Maybe we reuse it in the next step, and then this might be important. Okay. What happens with the stabilizer groups during these operations? So the stabilizer groups of the logical qubits, throughout this whole process, I've not drawn them, but they will not change because any logical operators commutes with the stabilizers. And if they commute and I measure that, they will just stay in the stabilizer group. And the stabilizer group throughout this measurement circuit on the right stays invariant. So we have now fulfilled both conditions. We have the correct transformation of the logical operators. Stabilizer groups are invariant. And this circuit on the right really implements the CNOT, the circuit on the left. If you want, you can do the same calculation using brass and cats. You will get just the same. That depending on your you will just get basically the same. Okay, question. It is necessary. Sufficiency, at least for Clifford operations, is also sufficient. For non-Clifford, so for anything that, for example, for the Hadamard, it's also enough because it's Clifford, yeah. For the T-gate, for example, it's more difficult, but I think it's also sufficient, yeah. Yeah, it might be more difficult to show because sometimes, like, operators may get mapped to superpositions of operators, and then, yeah, I wouldn't know how to, so sometimes, for example, for a T-gate, it's easier to show because it's in a Z basis anyway. To show this on a on the cats in the computational basis, that the logical basis states transform correctly. Okay. Now, I've said that the goal is that we want to perform the CNOT in 2D, but this still doesn't necessarily look 2D. I will show you on the next slide how it does, but at least it's not next to nearest neighbor. So you can still imagine that, okay, there's a control qubit, a ancilla qubit, a target qubit that kind of sit next to each other because this zero logical qubit kind of sits in the middle. And the way this is done in lattice surgery is the following. You place control qubit, the intermediate ancillary qubit, and the target qubit as such on a 2D plane. And what you can realize is, if you remember, the logical operators, they go in the different directions. So a X logical operator, for example, lives here on these boundaries, whereas Z logical operator lives on these boundaries. And now the crucial thing in lattice surgery, so here X ancilla, X target, is that in order to perform this first XX measurement, we can also initialize these intermediate qubits that are shown here in pink in a known state, and measure only four-body operators, four-body X operators. So instead of measuring, I could now also place one ancilla here and perform the X measurement using, that's 4 qubits. So let's just do it like this. Right, I could perform this joint logical X measurement using one ancilla, 1, 2, 3, 4. And let's say these are the qubits of ancilla and target, and perform this kind of measurement. But this again requires some degree of non-locality in 2D. What lattice surgery instead does, it decomposes those operators into four-body X operators only. Because if you now see those 4-body operators, they look exactly like stabilizers of the surface code, and the product of those 4-body operators. So if I have a 4-body operator X here, and I get the next 4-body operator X here, then on those middle qubits, they overlap twice, so they cancel to identity. Then I get the next 4-body operator X here, again on the middle. Let me see whether I say something wrong. One sec. Yeah. Okay. I measure these 4-body operators here, like this. Wait, wrong again. So these like this, and now everything is correct. Yeah. So I measure these 4-body or 3-body operators because now they overlap on the central qubit where they cancel to identity. They again overlap on this where they cancel to identity. And then I have the last one in this example where they cancel to identity. And out come only the X operator on these edges, which is exactly the product of, in that case, X ancilla times X target. Okay. So now in lattice surgery, what you do, to summarize, is because these operators live on the boundary, you can decompose it into smaller weight 4 operators that actually commute with the 2 patches, because the corresponding Z operators have even overlap with those 4-body operators. Plus, their product is exactly the X ancilla times X target logical operators on the boundary. So here you measure those, and then you do the same thing after that for the Z measurement, but on the other kind of boundaries here. And then in the end, you measure out your ancilla, and you can just do that by single qubit measurements. And then you have done this CNOT gate, all in 2D with only local operations. Okay. And this is like the reason that you can do this all in 2D with only local operations is one of the reasons why one of the many reasons why the surface code is considered as a promising architecture for example, superconducting qubits, where your connectivity is relatively restricted to 2D and nearest neighbor. But I will not talk much more about this, because if you're still here next week, there's gonna be a talk by Ilya, who was part of a team at ETH, where also Lucas was gonna be here next week, Louis, who's here, and my boss Marcos were part, where they actually took a superconducting surface code chip and realized such a lattice surgery operation. However, not in the surface code, but in 2 repetition codes, because they just didn't have enough qubits. But still, I think it's a really nice experiment. It was just published a few weeks ago. So look forward to this talk. Also, there's another talk about this next week, a little bit more general about lattice surgery in near-term experimental architectures by Lucas next week. Okay. Any questions to that part? If not, we come to the next subject, because for now, most of the noise models that we looked at, particular for the repetition code and then also later for the surface code, they just looked at this one layer of errors, and everything else was perfect. And there we knew that, okay, if our code has a certain distance, then we have a guarantee that a certain number of errors can be corrected. However, this is not really realistic. As you can probably imagine, if you have a real chip, lots of things can go wrong all the time. And this is the setting we're going to look at now. So every single component of our circuit can now be noisy. We again only use a very restricted noise model, which turns out to be quite powerful. So we use a depolarizing noise model. Or in general, people use a depolarizing noise model where each location, for example, state preparation, measurement, or single qubit gates can have one of X, Y, and Z errors using, for example, this depolarizing channel that you have seen already a few times, but of strength P. And also 2-qubit gates, or more general n-qubit gates, or more general n-qubit gates will have an n-qubit depolarizing channel. So in general, we could write n is 1 minus p identity plus 1 over 4 to the n minus 1 sum e in to the n without the identity. Yes. Identity row identity. Yeah. Thanks. P E row E. Okay. So this is the general noise model we're going to consider. We're going to consider X, Y, and Z noise, and also correlated on 2 qubits, because we can also treat it easily in using the same propagation rules as before. Now, if every component is noisy and everything from now on, as I already promised before, will be very high level without lots of equations, just to give you a feeling about that. But if every component is noisy, then we will have to encode every component in a fault-tolerant way. Fault-tolerant means comes in a bit. So for example, we will have to have a fault-tolerant state preparation. And then every of these components will be followed by some fault-tolerant round of quantum error correction where we measure those stabilizers and apply a correction. Now, this is only one model of fault-tolerant quantum computation. There's a few more, but this is like the most traditional model of fault tolerance, where also have been proven that even under circuit-level noise, there exist thresholds, particular by Alfieri, Gottesman, and Preskill in 2005. And the loose definition of fault tolerance is that if in each of those components, like a fault tolerant component is that if in a component we have T faults, where T relates to the number of errors we can correct for. So T, I'm just gonna write this here. So if we have distance D, then we can correct for T equals D minus 1/2 floor errors. So this is this T. And if in each component there are T faults, so let's say we have this QC block here, where we measure the stabilizer generators using Ancilla, for example, then at some gate there's one fault, and we do this correction, we want to make sure that in the end, at the end of this QC block, there's also at most t faults on that on the state, at most t errors on the state, because then a subsequent quantum error correction round of quantum error correction can correct this error. If, however, in such a gate, there's one fault, and we will have two errors in the end, then this might break the number of errors we can correct in subsequent error correction rounds, and we will not be fault tolerant anymore. And in particular, we will not get the scaling that I've shown you a few times, right? I've shown you that being able to correct for t errors implies that the scaling of the logical error rate in the small physical error rate regime is proportional to t plus 1, which is the first number of errors I cannot correct for. So if we can guarantee this, then we can call a component fault tolerant. If this is, it's not fault tolerant. That's our loose definition that we use now. And then we have to put it together somehow. And for that, IFRS Gosman Breskel, they introduced extended rectangles, which are those rectangles that we can draw about each component which it's trailing. Or let's look at this gate, which is with its leading and its trailing quantum error correction, round of quantum error correction. And if you then have in each of those rectangles at most t errors, then you can guarantee that your final computation after decoding is correct. And I'd like to note that we have this very final round of measurements, which we typically assume that we do a single qubit readout. And from the single qubit readout, for example, the Z readout, we can also reconstruct stabilizer generators and do error correction on that. Okay. Now, why do we talk about fault tolerance and circuit level noise? Yeah, I've already talked about this propagation of stabilizers and how errors X and Z, they can also propagate. One very canonical example of what might go wrong is that if we want to measure out, for example, a 4-body Z stabilizer in the surface code, we use one ancilla and couple it with CNOTs to measure, for example, the Z stabilizer here. Then if this gate is faulty, and after this gate, we have this Z error. This is one of those depolarizing errors that can happen with probability p over, for the 2-qubit gate, p over 15. Then this Z error propagates to a weight 2 data qubit error. So this breaks this assumption of fault tolerance that I've shown you before. So this would naively not be a fault tolerant implementation of the circuit, of the stabilizer readout circuit. And we might not be able to correct for that error, although we wanted to correct for T faults in our circuit. Now, one solution to that, already hinted on a little bit in the last lectures, is transversality. Transversality, means that we touch each qubit in each block with only one gate. Because then, for example, here, instead of using just one ancilla to read out the stabilizer, we use a full code block. So now up here we have the logical logical qubit, and down here we have an ancillary logical qubit, similar to in lattice surgery. And we couple this transversally with a CNOT and measure out Z. Then how can we do error correction with that? That's, by the way, called Steen error correction. First, I want to convince you that we can detect errors. So typically, if there's a Z error sitting on the data and we measure this the stabilizer, now this is this should be an X here actually. So if there's an X error sitting on the data and we measure the Z stabilizer, it will propagate to the ancilla and flip the measurement outcome to -1, so we can detect an error. The same works in this transversal approach. So if we couple this with a C0, then this gadget, the X errors get copied to this ancilla. And if we reconstruct Z stabilizers from these Z measurements, then the corresponding stabilizer, which the one that corresponds to this one here, will also have -1 eigenvalue. One small side note, this also enables, it's also loose, but instead of having to measure n-k stabilizers, we can just in one shot couple the data to the ancilla, do this transversal C0 in parallel, and in a more time-efficient manner read out the stabilizer generators at the cost of more space. The second thing I need to convince you is that this prevents this malicious propagation. And for that, I drew one fault here, the same as before, that propagates to a way 2 data error. The same fault on the other side, because every qubit is only touched by a single gate, only propagates to a single error on the data, and this single error can be caught by a later round of quantum error correction. So transversality, acting only on a single qubit in each code block, can give us a way towards fault-tolerant circuit constructions. There's a talk next week about fault-tolerant circuit design for near-term error correction by Sasha, who's a former PhD student in our group and now works for a startup called Next with a Q in there. I think in there or in there, I don't know. So there's probably gonna be a little bit more rigorous definitions and a few other examples on how you can do fault-tolerant circuit constructions. Of course. All right. Yeah. So transversality. Now we can now, for example, do if you believe me, all the stabilizer readouts with this transversal approach and have fault-tolerant syndrome extraction and fault-tolerant quantum error correction. What's missing is fault-tolerant gates. Can we also perform gates fault-tolerantly in this transversal manner? Now, I've written this no-go here on the right. Maybe, I will first show you which gates we've already achieved transversally. So the logical X and Z operators, they are always transversal. We have seen that, okay, other than these maybe constraints on how we want to implement the code, the C0 in CSS codes can also always be transversal and therefore naturally fault tolerant. Shown you, however, in the surface code, the Hadamard, if you remember, was not transversal. And also, there's this Easton-Knill theorem which tells us that no quantum error correcting code can have a transversally universal gate set. But maybe we can like get a little bit more transversal gates. And for that, I want to show a different topological code for a few minutes, where I hopefully can convince you pretty fast that this has a transversal, a nicer transversal gate set than the surface code, namely color codes. So the surface codes, if you remember, we put the qubits on the vertices of a lattice, and then we had these two kinds of stabilizers, Z on the plaquettes and X on the stars, for example, with X and Z logical operators, which prevented us from applying a transversal Hadamard because, the locations of X and Z stay interchanged. Now, if we had a code where each stabilizer, where all the stabilizers are X and Z on the same qubits, and all the logicals are also X and Z on the same qubits, we would not have this problem. because then a transversal Hadamard will just like transform an X into a Z that already exists in a stabilizer group and the other way around. And if you do this on a tricolorable lattice, where you put the qubits on the vertices as such, so here on this tricolorable lattice R, G, and B, we put qubits on the vertices, then you can define such a code. We now put X and Z stabilizers on each of the plaquettes, so act on each qubit around the plaquette, and you can make sure that also, and the tricolorability makes sure that these stabilizers commute because they all have even weight. So these and all the other plaquettes on this tricolorable lattice have an even number of qubits. So if you do X and Z on those, they overlap an even number of times and they all commute. In addition to neighboring plaquettes, for example, if you look at this interface here between this green and this blue plaquette, this is a red one and this is a green one, then they overlap on 2 qubits always. If 2 stabilizers, X and Z, overlap on 2 qubits, twice anti-commutation gives us commutation again. So on such a lattice with these stabilizer generators, we have defined a code where we have X and Z on each plaquette with the same support, such that if we now apply a Hadamard, the stabilizer group at least is invariant. And indeed, the logical group on the logical level, we will perform the right action, which I will now try to convince you with the smallest version of this color code, which is the 713 code, or also called Steen code, where we just have 3 of those plaquettes of 4 bodies. We have a total of of 6 stabilizer generators, all 4 body X and 4 body Z. You can then count 7 qubits minus 6 stabilizer generators, 1 logical qubit remaining. And logical operators, for example, could be X and Z on all physical qubits. Why does this work? You can try to multiply X and Z stabilizer generators, and you will never be able to construct these operators, so they are not stabilizers themselves. Plus, they always have even weight because they have weight 4 and they overlap on 2, so every product of them has even weight. Those have odd weight, so that doesn't matter, but they always have even overlap with this operators, and then they commute with all the logical operators. And now here you can already see, if I apply a transversal Hadamard in the following way, then the operators, the X and Z logical operators, they just transform into each other. The same holds for the stabilizer generators, but the generating set, we can choose another generating set. In that case, it's also just labeling the stabilizer group. In total stays invariant, and this transversal application of the Hadamard implements the logical Hadamard. Okay, what I didn't show you, but there's also a way in these codes to implement the transversal, the S-gate transversally. And then in these codes, we have the full Clifford group transversal and naturally fault tolerant. That's already quite something. The question is, can we get the T-gate? And the answer transversally in this code, and the answer is no. If you're interested, check out this reference on why you cannot get the universal gates transversally. However, there's ways around that. I've shown you the gate teleportation circuit yesterday with the Hadamard. If you replace the Hadamard with the T-gate, you have to do some other transformation in the circuit, but in principle, you can then also implement the T-gate with the same approach by starting with some resource state and doing Clifford operations only. One way I want to advertise, because we've also have some people in our group working on that and also working on experimental implementations of that, is code switching. So I've always told you that we want the logical gates to keep the stabilizer group invariant, but nobody prevents you from starting in one code and somehow transforming into another code while taking the logical information with you and then continuing in that other code. Code switching is an approach where you then, for example, start in this color code, scene code that I've shown you now, where you have the full Clifford group transversally, and then at some point you switch into another code, for example, this 3D color code, which has another transversal gate set. For example, this code actually implements the T-gate transversally. So you start in one code where a certain gate set is transversal and fault tolerant. You have to switch to another code where another gate set is transversal, and then you get a full fault tolerant transversal gate set. This may sound too easy. It's also not easy because the switching process itself has to be fault tolerant, which is a big challenge. But yeah, if you look at this paper or also just Google code switching, there's ways to get this fault tolerant. Okay. Next, I want to give you a small glimpse into the future, maybe the future, on quantum LDPC codes. All the codes that we've looked into now were either the repetition code, this concatenation of the repetition code with a Hadamard version of it, this 9-qubit Shor code, the topological toric and surface codes, which were using only nearest neighbor connectivity, either with periodic boundary conditions or with on the surface, or also now this color code. It's also a topological code where you can, with low connectivity requirements, achieve get your error correcting code. Now, if we want to take this code and scale them up, for example, the surface code, here this is the smallest example of a surface code with a distance 3, so we can correct for one error. We have to take, as I've shown you yesterday, no, day before yesterday, we have to increase the linear dimension of the lattice to get a square root better protection in the distance. But if we get larger and larger, we will still always only encode one logical qubit. So the overhead required to better protect one logical qubit grows quite substantially. However, this is the optimal way in 2D. There's this theorem by Bravi, Poulin, and Terhal that tells us if we have only if we have a code that we can embed on a 2D Euclidean lattice, then we cannot get better than this scaling. How can we, however, get this k larger? Yeah, we can just take copies of our code. So for example, take L copies of our code, then we have a, in this case, a 13L3 code. We can then play a little bit around, but the best balanced scaling we can achieve is proportional in 2D, has some 1/3 factors on the k, on the number of encoded qubits and on the distance, which is still a big overhead. Now, in classical computing, you also use error correcting codes. And there, for a long time, people have known that if you want to encode k classical bits in n classical logical into n classical physical bits with a distance of d, then you can just write down a random matrix, and with high probability, if you take n larger, then you will get a code that has a scaling of n, order n, order n. which is much better than the scaling in the quantum case. So people were wondering for a long time, if this is possible in the classical world, can we also get the scaling in the quantum world? Here I have a little landscape of quantum codes where I now put the rate, so the ratio of encoded information to the number of physical qubits on the x-axis, and the distance, so the protection against errors on the y-axis. And yeah, the field started basically with topological codes, which had a quite good, the square root of n distance protection, but asymptotically, the rate goes to 0. So asymptotically, one over n goes to 0 as n goes to infinity, or even, let's say, some constant over n goes to 0. Only in 2009, Jean-Pierre Tillich and Seymour, they found a way to break the they found a way to construct codes that actually have a constant encoding rate, quantum codes. Constant encoding rate meaning they managed to get quantum codes with parameters n, k of order n, and they also found a d of order square root of n. I will show these codes in a little bit, but this was already substantial progress to find such codes. However, the distance was still bounded by the same scaling of the distance as topological codes have. And then only a few years ago, with G-lifted product codes, balanced product codes by Nico Breukmann, and quantum Tanner codes by Anthony Leverrier and Seymour, they also broke this barrier. And now we also have quantum codes that scale in a good way. So we can actually have a constant encoding rate and a very good distance protection in the asymptotic limit. Okay, however, so this is a little bit an old slide. There's now also codes that have a little bit smaller qubit numbers representatives, but this good scaling typically is achieved with very high encoding rates, with very large qubit numbers. And everything that happens in between here, kind of you can think of as lives between the bounds of Bravais-Poulin and Terhal that actually showed these bounds not only for 2 dimensions but for arbitrary dimensions, and showed that okay, in order to get this good scaling, you will not be able to be embeddable in a constant dimensional Euclidean lattice anymore. So you have to give up this 2D locality in order to get better codes in some sense. Okay, in the last 10 minutes, I will use my time to advertise some own work. And the latest work that is out there on quantum LDPC codes, and then also show one more thing. Okay. So at the start of my PhD, we were looking into these QLDPC codes and tried to go a little bit only beyond surface codes. So we constructed something called lift-connected surface codes. And these codes are not 2D local anymore, but 3D local. And you can think of them as you take these surface codes and stack them in a torus, and then every stabilizer generator, instead of measuring just 4 neighboring qubits, you also measure one of your left and one of your right neighboring surface code. So you lose some locality, you get some more connectivity constraints, but you can, it's regular code. You have X and Z stabilizer generators. You can do the same, play the same game as before. So for example, you can write down a circuit that measures stabilizer generators. This is now for an example which has 15 physical qubits, encodes 3 logical qubits with a distance protection of 3. And then we can perform these measurements. We can do simulations to find how good will these codes perform. And we found that if we use, for example, just 15 physical qubits in these more non-local codes compared to surface codes, we get the same protection against logical errors, approximately the same protection, compared to a surface code which uses 3 times more physical qubits. So not only does this, so there's a trade-off. Of course, we introduce some non-locality, but we can encode more information into fewer physical qubits, and therefore, in a circuit-level noise model, get a similar protection using fewer physical qubits. Or you can also think of it as we can reach the same logical error rate using a smaller overhead, using this non-local codes. Now, not only we worked on that, also IBM is actually very much invested in quantum LDPC codes. And one of their idea is to use slightly different codes. They're called bivariate bicycle codes. And they've already built up a big roadmap on how they might implement those bivariate bicycle codes in the architecture, where they also show, as you can see here on the right, using those codes compared to a surface code architecture under assumptions on how you'll be able to implement these non-local connectivity required, you can actually get a higher number of logical qubits with the same quality compared to surface codes. One very recent work by theoreticians from Sydney, they also use different kind of quantum LDPC codes and build up a full platform, so incorporating all of the elements that I've shown you: logical gates, stabilizer measurements, a compilation pipeline, on how you would get a actual quantum algorithm onto such a quantum computer. And they showed that they can now, or they claim that under certain assumptions on noise and on implementability, that they can use Shor's algorithm to break RSA-248 using only 100,000 physical qubits. Now, this made quite some noise because the estimates before were 1 million physical qubits, and the estimates before were 10 million physical qubits. But yeah, as I've said a few times now in the last 5 minutes, there's always trade-offs between what you can actually build and what us theoreticians imagine might be possible one day. Okay, so quantum LDPC codes is one very promising approach for the future. I want to present one more advanced concept, which also considers constraints on platforms a little bit more, which is measurement-free quantum error correction. So again, this picture here, you can now imagine errors anywhere and not only on this layer, but we typically use this error syndrome measurement to get information about the errors, then use some decoder to infer correction, and then correct for our error. However, there are multiple platforms, for example, neutral atoms, where measuring qubits is very slow compared to implementing gates. Also, even if measurements might be feasible, you still need to measure, you need to compute the correction, you need to apply the correction, all this while keeping your quantum state alive. So these are big challenges, and wouldn't it be great if we could just do this whole thing in quantum, and instead of having to measure, we just discard our ancillary register. Now, there will be no way to not use an ancillary register in some way and to discard in order to get some entropy out of the system, but typically resetting a qubit in platforms can be easier than measuring. Just imagine if you want a good resolution for your measurement, ion 0, ion 1, you might have to scatter a lot of photons. However, for reset, it might be enough to scatter a few photons, because you don't care about the measurement, about the actual measurement outcome. So challenges the main challenge motivating measurement for error correction is the technological challenging measurements. However, on the other hand, implementing or devising protocols that are measurement free is also quite challenging, considering all these fault tolerance considerations that I've conveyed today a little bit. However, if you want to know more about that, Katrin has a talk next week where she will at least show one small application of and one small circuit of measurement-free error correction. One thing orthogonal to that a little bit is if you ask the question, instead of realizing an error correcting code that doesn't use measurements at all, you could also ask, okay, I have measurements, but I don't want to connect to so many qubits. So can we also do error correcting codes with low weight measurements? But then we might need more of them. And there, this is the realm of Floquet codes, or of dynamically generated codes, which was pioneered by Hastings and Ha, where you, for example, only use two-body measurements all the time. So instead of having those 4-body or those 6-body measurements that I've shown you for the surface and quantum LDPC codes, you just use 2-body measurements and reconstruct from products of 2-body measurements bigger operators which you use for error correction. Okay, this is just that you know that this exists, and if you're interested in that, you can come talk to me, or you can just Google and find some results. Other than that, I just want to quickly summarize what we learned in those 3 lectures. We learned about the basics of quantum error correction. You now know how you can write down quantum circuits, how you can find out what this quantum circuit does using, for example, a stabilizer approach for Clifford circuits. We learned about stabilizer error correcting codes. How can we correct for errors? How can we implement logical gates in those codes? How do they protect against errors? What are the challenges when we implement those circuits and those logical gates using actual circuits and more realistic noise models? And then finally, I've shown you a few outlooks on more modern approaches. And with that, I want to thank you. Thank again my group, my supervisor, Markus Müller, the organizers again, and I hope you have a good lunch. I hope you have a nice week. And if you have any more questions, please don't hesitate. Thank you.